Okay, now here is the key photoelectric formula, photoelectric effect formula or equation that we will be utilizing to do a lot of the work there. Now, before we talk about this, remember we have what we call the law of energy, which says that energy cannot be created nor destroyed. It can only be transformed from one form to another. So when energy is involved, you can't destroy it. You can only transform it from one form to another. For example, when a car is speeding down a highway and then it hits something, the kinetic energy, which is the movement energy of the car, will be converted into, number one, heat energy, which is why sometimes the cars burn. Number two, it will be converted into what we call sound and light. So other forms. That's why when something or when an accident happens, you can hear the sound of the car crashing to the other or to the object. So that is conversion of sound, of kinetic energy into other forms of energy. So now let's look at the one we are dealing with. The energy of incident light that is shining on the metal is going to be then broken down into energy that is required to overcome the work function. So some energy will be used just to overcome the work function, as we looked at it before, to overcome the bond energy of the electron to the metal. Then whatever energy is left over is going to be converted into kinetic energy of the electron. So it's going to be what the electron has to speed out of the electron, out of the metal, going into our circuit. Now, don't forget that EK is equals to half m, here m of electron, v squared, but the velocity again will be of the electron specifically. So it's half mv squared, but we are talking about electrons. Now here, please do understand that energy can be calculated as Planck's constant times the frequency of the light. So the frequency of the light, when we know it, we just multiply by this number called Planck's constant, we get the energy. So that's a conversion between energy and frequency. The Planck's constant is a given. It will be given on the formula sheet or information sheet as 6,63 times 10 to the power negative 34. So that's what we're going to be using. Now let's just go back and check this. Please, do you remember or can you recall the order of the colors of the rainbow? It is important that you do. You need to know that the order of colors of the rainbow is Roy, G, Biv. Where this one is red, orange, yellow, green, blue, indigo, violet. Okay, for now we don't need this explanation. I need to write something else there. But please remember, this is the order. Why do we want you to know this? Because we want you to know that red actually has the lowest frequency. Red has the lowest frequency. Violet has the highest frequency. But because frequency is inversely proportional to wavelength, red actually has the longest wavelength. Violet, on the other side, has the shortest wavelength, because your wavelength has to be short for you to have a high frequency. So shortest wavelength. So this is important because there are some questions that can come and try to trick you here. For example, they'll tell you that, please do explain why when red light was shown on a metal, there was no current. But when blue light was shown in the metal, there was current. Then you can quickly explain that red has a low frequency, so the frequency must have been less than the threshold frequency, or its energy must have been less than the work function. But when blue, which is light of a higher frequency, was shown on the metal, it was able to then eject electrons out because it had an energy more than the work function. Then of course indigo and violet will also do the same, but definitely with a higher speed of electrons, because more energy would be left over to be converted to the energy of the electrons. So this here is the photoelectric effect formula or equation, explanations of the constants that are there as well as the numbers that are there. So this one can be broken down to the HF that we are seeing here. This one, on the other hand, can be broken down to HF0, where F0 is the threshold frequency of the metal that we are talking about. And also please do note, this depends on the metal. If you don't change the metal type that you're working with, this never changes. Whereas light, color can change. So if color changes, frequency changes, meaning the energy changes. So that's what we have. Remember, white light actually contains all of these ones. Therefore, white light is the most superior type of light. Carry the white light forward. Let's go on. Okay, before we go into the questions and deal with issues of intensity of the light and other things, let's look at the formula in the expanded format. So, energy of light is equals to W0 plus EK. Also, this means that when we take the Planck's constant times the frequency of the light, it will be equal to the Planck's constant times frequency or threshold frequency of the metal. Then whatever else is left goes to the half mv squared. The ME is a given number. We have it in the formula sheet as 9,11 times 10 to the power negative 31 for the electron mass. It's given. You don't need to memorize it. Just remember to check your formula sheet for it. Then this one would be the velocity of the electrons, because sometimes they ask you to calculate the exact velocity of electrons. So we can use this formula for that. Now, just the final conversion. Remember that we had the key formula which said that C is equals to F times lambda, now, which is wavelength. Now, frequency can be taken as speed of light divided by wavelength, which is why we say there's an inverse proportion here. The larger this number, the smaller the frequency. The smaller this number, the higher the frequency. So therefore, we can also have F0, which is threshold frequency, and this one can be threshold wavelength, because sometimes they give you formulas that have threshold wavelength, although it's not based on our key definitions. It's a definition you can deduce from everything that we've discussed. So this is what we have, so that we can then go on to talk more. Now let's just talk about intensity of the light, as we have already talked about frequency. In addition to the frequency analysis, intensity is another key concept that they check on. You will check past papers, 8 out of 10 past papers that you do have a question on intensity. Now, intensity is talking about the brightness as well. We can just refer to brightness of the light. Now, let's understand what happens when you shine a light brighter. Higher intensity means that you have more photons moving, which is why when a car during the night has its dim lights on and then suddenly brights you, it means that more photons are coming at you, which is why then your eyes have a problem, or you then have your eyes having to accommodate the higher light. Some can't even see in those kind of conditions. So intensity means more photons are falling on the metal surface per unit time. Therefore, more photoelectrons are ejected out of the metal per unit time. So more electrons are ejected. We call those photoelectrons. Just key concepts and terminologies that are used interchangeably in the papers. I want you to have them. Then if we have more electrons per unit time, it automatically means our current will be more. So more electricity is generated. Whereas the other side, if low intensity is used or lower intensity, lesser photons will be ejected, will be incident on the metal per unit time, meaning that less electrons will be ejected from the metal per unit time, so our current will decrease. So you know they love it in physics. They say, explain what would happen if intensity is increased. Choose from increase, decrease, remain the same, and then explain the reason for that. Then you would say that if it is increased, current increases. Reason, more photoelectrons incident on the metal, therefore more photoelectrons are ejected from the metal surface and more current. Just to confirm something, please, in the relationship between the photons and the electrons, please know that each photon collides exactly with one electron. Therefore, it's a 1:1 relationship, meaning that if you find the number of electrons, you can actually find the number of photons. This is key, because in some cases they will want you to calculate the actual current induced or give you current, ask you about the number of electrons or photons. This is the key equation together with those that we saw for the charge and current. So please do understand this one, photoelectric. If you have questions about it, share on the comment section, I'll attend to you. But overall, we will go into some past papers and understand that generally we use a cell that looks like this. We'll have the ammeter there. Then here we will have a collector. Sometimes they show us the battery that is going to be connected and charged using this here. Then the light is shown onto here. You will see the past papers when you look at them. The reason why this is curved like this is so that when the electrons are removed, they are going to be removed in a perpendicular manner so that the collector can have them. Remember that we have this particular case that concave shapes, they allow us to bounce things off such that even if the light was to shine on here, then the bounce back would be all the way up here, because then it's a more upward bounce. But those are technicalities, you won't be asked about that. It's just for me to explain to you why the cells or the diagrams are as they are. It's for practical uses. That this allows us to collect as many electrons as possible that are ejected so that they don't fly off and we don't get the electricity we want at maximum. That's it. Photoelectric effect explained. We will get other questions that you might have, of course. We will address them and whatever else is not clear. But from here, past papers.